Welcome to my new calculus channel. My name is John Gabriel, and today we're going to be covering propositions 7 through to 11 of Euclid's Elements and Book 5. So let's begin. Now, in proposition 7, we're told that ratios are equal if and only if their antecedent and consequent magnitudes are equal. And of course, this is further clarified in subsequent propositions. But proposition 7 states it in this particular way. It says, in other words, ratios that are in proportion may not of necessity be equal also. So they may be the same in terms of proportion or quotientness even, but not equal. And I have mentioned earlier that it is insufficient to call ratios equal unless their corresponding aliquot parts are also equal. So from proposition, we see that an inverse excludes zero magnitudes again, because inversion would not be possible if we had zero as a number, right? So, and we also know that zero cannot be part of any ratio, because to be part of a ratio, you have to be comparing two magnitudes, and zero is no magnitude. You can't compare it to anything. So the property of trichotomy of magnitudes, which is introduced gradually, starting from proposition 7, is telling us that the comparison of ratios that are not proportional is stated in terms of dichotomy. In other words, if we don't really care if they're equal or not, we can say whether one is bigger than the other. Okay, and that's what proposition 8 is going to tell us. But before we go to proposition 8, just note that proposition tells us if we're given A proportional to D and B proportional to E are equal, then if C proportional to F is proportional to both these, then it follows that F is either less than, equal to, or greater than D. Okay, so it's a loose form of trichotomy. This is what you can conclude from this proposition. And in the case of equality, which it doesn't care about right now, C would be equal to A and B. So let's see what proposition 8 says. Okay, so proposition 8 tells us about how one ratio can be considered greater or less than another. So now we actually come to a definition in terms of sizes, measure. The ratio is not really greater or less, but the measure of the ratio is either. Remember, ratios cannot be greater or less at all. Okay, they can only be in proportion or equal and in proportion. Okay, so of course if they're equal, it follows that they are also in proportion. Now proposition 8 tells us that if we have magnitudes, as we see here, this red to this blue, it's going to be less than the same red to this shorter green, right? And likewise, this blue to this red is going to be greater than this green to this red. And if you look at it using numbers, it makes sense, because 8 to 4, the measure of 8 to 4 is 2, and the measure of 8 to 2 is the measure of 8 to 4 is 2, and the measure of 8 to 2 is 4, and 2 is less than 4, right? And half is greater than a quarter, isn't it? Half is greater than a quarter. But we're talking now about the measures of the ratios. This is not saying that this ratio is actually greater. You cannot say a ratio is greater or less than. There's no such thing. They're either in proportion, or they're not, or they're equal. Okay? One of those three things. As a matter of fact, if they're equal, they're automatically in proportion. So this proportion leads to the next, where it's stated unequivocally that the only case when two ratios are equal is when their corresponding aliquot parts are equal, regardless of their quotientness. This leads to the completion of the trichotomy property, where equality is defined. So in proposition 9, we see that magnitudes having the same ratio to the same are equal to one another, and those to which the same magnitude has the same ratio are equal. So what it's saying is that proposition 9 completes trichotomy with the inclusion of the property of equality. So therefore two ratios are only ever equal if their corresponding aliquot parts are equal. And of course then also their measure will be equal. okay? But they don't have to be equal for their measure to be equal. So Heath fails to define this properly. For example, ratio P to Q is equal to R to S if and only if P is equal to R and Q is equal to S. For otherwise, all we can say is that either of the ratios have a proportion with each other, or we can talk about the quotientness of each individual ratio. Now, proposition 10 tells us the inverse of proposition 9. That means proposition 9 says P is equal to R and shows that Q must then equal S. On the other hand, proposition 10 gives us or tells us that Q is equal to S and then shows that P must then equal to R in each case, so that one can say that P colon Q, or P in ratio to Q, is equal to R in ratio to S in terms of not only measure but in terms of ratio as well. Okay, so this is a special case where the ratios are equal and their measures are equal. Okay, but you can have ratios which are not equal and their measures are the same. Finally, proposition 11 does not say ratios are equal, but they are proportional if their aliquot parts have a proportion that is the same. Okay, so it's a further clarification. So let's look at let's see what this says exactly. If their aliquot parts have a proportion, they're the same, but not in the sense of equal. For example, an apple and an orange are both fruit, yes? So they are the same in this respect. They are both fruit, but they're by no means equal because they're not the same thing. So 2 in relation to 4 is proportional to 4 in relation to 8, or in proportion to 8, because 2 is to 4 as 4 is to 8. And so in terms of measure, they are considered to be the same, but nowhere does the word equal appear in the proposition, okay? It says the same. They have sameness, but they're not equal, okay? It's 2 different things. So whenever there is any doubt about what the proposition says as you study the elements of Euclid, it is always a good idea to study the part where Euclid writes "ego leo," or "I say that," ... So in this case here he says, for let it be that as A is to B, so C is to D, and as C is to D, so E is to F. And then I say that A is to B, I say that as A is to B, so E is to F. Okay. In other words, the conclusion is this, that if you have 3 ratios in proportion, then the first ratio will obviously be the same as the last ratio. Okay. By transitivity of proportionality in this case. Not transitivity of equality, but transitivity of proportionality. And that, my friends, are the first 11 propositions. So we're going to be spending a lot of time on proposition 12, the most interesting proposition of book 5, and I say with all authority, the most important proposition of all the elements, okay? Because it's in proposition 12 that we'll see how all the algebraic, all the arithmetic operations come together. So stay tuned, look forward to that, because that's going to be very interesting. And I'll leave you with those thoughts. I hope you enjoy the previous video I uploaded. It's a discussion I had with Mac Fry about a lot of different topics relating to mathematics and the foundations, the philosophy, the pedagogy, etc. And it's an interesting video. It's a little on the long side, so if you get a chance, set aside some time to watch the whole thing. It's very interesting. Well, my name is John Gabriel. This is a New Calculus channel. Till next time, goodbye.